Hi, my name is Mustafa Bayramov, and the goal of my talk today present my CS236 project. So the main objective of my project to explore generative models for the graph generation, and the main motivation behind that explore specifically the modeling aspect related to generating graphs that are very close to geometrical shapes. Specifically, my primary objective was, can I generate a set of vertices that very close to original shape of a graph? So for example, if it's a point cloud or any geometrical object. And the secondly, can I create a model that take existing representation, for example, point cloud object, and represent that in the graph structural information and learn the shape of a graph and describe object itself. So the graph generation is a very large topic by itself. We can explore graph generation in the context of biology, engineering, and the social science. For example, there was a number of attempts to create a model that can generate the molecular structure information. Generally speaking, the graph generation and modeling is a very hard problem, and it's due to a couple of factors. The first one, and probably the most obvious one, we don't have a fixed structure of the graph. And the secondly, the graph generation need to cover very large variable output space. So we can imagine, we have an n-square problem, since most of the graph representation that we use in the modeling, it's a dense matrix representation. So without going into too much details, the main objective generate a graph that are very similar to real graph, and it's a domain-specific task. So the first goal was to explore idea already described in the graph RNN paper and the framework, and an attempt to improve a model. In graph RNN settings, we can describe a generation process as autoregressive and recurrent. In essence, it is a sequential model that tries to capture joint probabilities for all the vertices and edges in the graph. In these settings, we use two parallel networks, and each network is responsible for producing a prediction for the edge and the node in the network. In essence, one network used to generate a set of nodes in the network, and the second network used to produce the edge in the network. So immediately one might ask how the network can predict the edge between the set of nodes. So idea export in graph RNN, it uses the BFS node ordering. In the second model, I evaluated the implicit generative model, and in these settings, the graph generation problem is a problem of learning the distribution of a biased random walk over the input graph. In this model based in the stochastic neural network, and it generates discrete output samples, and it uses idea described in Wasserstein-Gunn. So the core idea lies on capturing the topology of the graph by learning a distribution over the random walks. Similarly to any GAN architecture, NetGAN consists of two main components, a generator and a discriminator. On the poster on the right corner, I capture the essence of the model. So in these settings, the authors describe the main objective for generating a synthetic set of random walks that are pausable in the input graph. And at the same time, the discriminator learns to distinguish the synthetic random walks from the real ones that comes from the training set. In my project, specifically, I've tried to focus on two aspects: how I can improve the sampling, since the graph RNN is very slow to train and very slow to generate the samples. And the second major issue with the training is generally how you evaluate the system. I use the same dataset that the graph RNN used. Specifically, I focus on the shapes such as grid, triangle-based faces. I have attempted to represent the cloud object as well by leveraging K-clustering algorithm and sampling in the graph representation. The metric I've used are similar to the graph RNN. It's basically degree of the nodes, orbits, and the graph similarity. I also developed a system that output epoch by epoch graph as an image to a tensor board that essentially allows me to see entire graph generation process and do visual inspection. Secondly, all the models can be extended in many different ways. For example, the BFS order for each sampling can be augmented, and for that I developed a modular platform that I can augment any specific component of a model. So for example, I can augment BFS order to the random sampler or random walk sampler in the graph RNN. Lastly, I decomposed all the models from the training itself that allow me to track sample time and many other metrics. In summary, both models learn graph representation. Both models generate the graphs that are very similar to the training set. For example, grid with 100 vertices in graph RNN settings converge in about 1000 epochs with a batch size 32. Meanwhile, graph RNN approach significantly slower. I made number of modifications to original model to speed up generation and reduce number of the epochs. And lastly, it's issues related to the sample time because it's very slow. In terms of the future work, there are a number of areas that needs to be explored, in my opinion. One is a parallelization. In essence, explore ideas already developed in the natural language processing and related to attention methods. Secondly, improve the heuristic related how age prediction in the systems. For example, I try to explore ideas parallelization in terms of the BFS ordering in order to reduce the time during the training process. And the same for the prediction. Thank you very much.